Analytic solutions. We have seen that there are two basic types of analytic solutions, geometric solutions and algebraic solutions. We will start with geometric solutions. They are applicable to robots with few degrees of freedom, such as 3 degrees of freedom or less. If robots have more degrees of freedom, it can be applied to the first 3 degrees of freedom, if the other degrees of freedom are only used for orientation. However, it is not a generic solution and it depends on the robot. That is, there is no generic procedure to solve this. You have to do it case by case. Let's see a simple example. We want to find the inverse kinematics for this robot, for the position of this robot, using a geometric approach. Let's consider first joint 2. For joint 2, that's to say this Q2, how can we find it? In this picture, you can see that here this angle is 180 minus Q2. So you can have this angle, this length L1, this length L2, which are constant, and you can also have a new line here, which can be L. This L is basically obtained as the modulus of this x and this y. So here you can see that you have a triangle, and this triangle gives you the identity called the law of cosines. So using the law of cosines, what you can do is this, that this length L squared is equal to L1 squared plus L2 squared here, minus 2 times L1, L2, times the cosine of the angle that you have here, and the angle here is 180 minus Q2. Then you can already solve or just express this L in terms of x and y, because this L is x squared plus y squared, and that's what you have here. Then this cosine will become just cosine of Q2, and here you change the minus with a plus, and then you can solve for this Q2, and you can easily get cosine of 2. Now if you use a trigonometric identity, we have that sine squared plus cosine squared equals 1. So from here we can solve for the sine, and you will have that the sine is plus minus the root square of 1 minus the cosine squared. Now you have the cosine for the second angle and the sine for the second angle. What you can do is you can use the arctangent. As I said before, you usually want to use the arctangent because it preserves all the quadrants. Now for Q1, we can also use the geometry of this figure. For example, we have here Q1, and here we can say that this little part will be angle beta, and this part will be angle alpha. So we can say that Q1, as you can see here, is this alpha minus beta. Alpha can be easily found because alpha is just this angle, so it's the tangent of this y over this x, which is what you have here. For angle beta, it's not so easy, but if you do this, if you get this triangle, now you can see that beta is this over this, the tangent is that. So this part is L2 sine of Q2, and this part is L2 cosine of 2. So beta is going to be the arctangent of L2 sine 2 over this L1 plus L2 cosine 2, which is what you have here. Now you can just replace for Q1, and you have this alpha, which was this expression, minus beta, which was this expression, and Q2 is this. And so now we have found the solution for this robot using a geometric approach. Algebraic solutions are solutions that use algebraic and polynomial equations. Again, they are ad hoc solutions, so there's no general procedure. As an example, let's see the same example that we saw before, but now using the algebraic approach. From forward kinematics, we have this expression for x and for y. You can see that now we have the cosine of 1 and the cosine of 1, 2, and here we have the sine of 1 and the sine of 1, 2. So we have the cosine and the sine of the same angles. One trick consists in squaring this, because if you square this, then you would have cosine square, then sine square, and if you sum those, then the cosine square plus sine square will just be 1, and then you will be able to eliminate that. That's what we're going to do. So for Q2, we square x and we square y, and then we sum both terms. If we sum both terms, we get this, where we have eliminated this because it's cosine square plus sine square, also here cosine square plus sine square, so we only have L1 squared plus L2 squared and all this expression. We can also simplify this expression, and this leads us to this, well, using the identities of the cosine of two angles and also for the sine. And from here we can solve for the cosine of Q2. And this is exactly the same expression that we also obtained before. For the sine, we can again use this identity, and we can solve for the sine, and then we have sine and cosine, so Q2 will be given as the arctangent of sine and cosine. For the first angle, now we're not going to do any geometry here. rather what we're going to do is we're going to expand both terms of forward kinematics. So we expand these two terms, and now we see that these expressions are linear in cosine 1 and sine 1. So we can reorder them in this way. We put cosine 1 here and sine 1, and for y we put sine 1 here and cosine 1. And then we can put this even in a matrix form, which is this one, and we will solve for cosine 1 and sine 1. If we solve for these two, and this is a matrix, a linear matrix, so we can solve for these two elements, we can easily obtain the arctangent, which will be our solution. Now, the solution for this is cosine and sine are these expressions, where that is the determinant given by this new expression. Let's see another example. Let's consider a 3-degree of freedom robot where its end effector pose with respect to its base is given by this expression. A3 and D1 are constants. The desired pose is this matrix T des, and we want to find the inverse kinematics as a function of the elements. That is, we want to find the inverse kinematics as a function of these elements because they are considered to be numbers. For this case, the procedure will be obtain some relations between both matrices and then apply some algebra. Again, this is an algebraic approach, so there is no generic solution. It's a case-by-case solution. If you compare from the previous matrix, we can do this. For Q1, we have Px, which is this expression, and we also have Py, which is this expression. It would be useful if you compare these expressions with the previous matrix. From here, we can solve in this way, and from here we can solve in this way. Why do we do this? Because now we have sine and cosine. We can divide them and we have the arctangent. That is, we can have the tangent of this, which is the division between both. We can replace this C13 with this nx. You can see that from the previous slide. And at the end we have a θ1 is the arctangent of this expression. For θ3, we can also try to compare terms, and we see that this holds. If we divide this term ax divided by nx, we have the tangent of θ1 plus θ3. From here we know that θ1 plus θ3 is the arctangent of this, and then we will have that θ3 is this arctangent minus θ1. But we already know θ1 from the previous expression, so this is already solved. Finally, for θ2, we have this expression which is the same as this one, px, and we multiply it with sine. So we have sine here and sine squared. For y, we do the same thing, but we multiply with the cosine. Why? Because we want to have again sine squared and cosine squared, so that if we sum these two terms, then they will disappear. And that's what we do. But in fact, we are taking the difference because these two elements have a different sign. So we take the difference, and this term will be gone. We will just have Q2, and Q2 is what we want. So now we just solve for Q2, and that is our solution. See that Q2 is a function of Q1, but it's not a problem because we already computed Q1.